I will record it.
Okay.
So let's get started. So Finn Atkins is here today. He's going to be giving a guest lecture. He's going to talk about a formal verification framework called TLA+, and he's going to talk about that in the context of his work. So you're going to get to see not just how you use formal verification, but how he's using it in a particular, actual, real, cutting-edge research system.
Right. Okay, well, hi. So thanks for having me, Tony. Welcome to essentially a recreation of some talks that I've given somewhat recently. I am shamelessly reusing those slides, but I think they're equally appropriate, and I've extended them with some interesting little demos here and there because I have a much longer time slot here than the original presentation. So nominally, these slides are about our project called OmniLink. Fun fact, Brian is actually working on this. He's in the back over there. Shout out, Brian. And this is an ongoing project we have, which, again, like Tony said, has a specific purpose. But I will initially talk about what even is TLA+, and like why is this project a thing, and let's go. I said, let's go.
You have to move the mouse back. I started recording.
Oh, okay.
So, yeah. Now
Gotcha. Okay. Cool. Thank you. So, yes, thank you. All right. So, the basic premise of this is concurrency is really hard to deal with. This is not something we find convenient. Excuse me one moment while I fix this unfortunate thing where my power saving will otherwise do not. Screen blank. Thank you. I'm sorry. Normally I remember to do that. My bad. Okay, back to what I was talking about. So now the demo computer is safe. Concurrency is generally a pain. You'll have learned about this perhaps in 213, assuming many of you will have taken this. It's possible not to. You could have transferred. But basically, when you have multiple threads of execution, all of a sudden, code that looks like it goes in a straight line and does a specific thing, with the same inputs, will do all sorts of different things. And it loves to surprise you, especially in the middle of the night when it crashes your server and you have to wake up and reboot it or something, depending on what you're doing. We see these all the time. You can come up with a whole board of news clippings of things that were more or less caused by various strange, unforeseen interactions between events and stuff. So these are interesting in the fun sort of way where no one really has a choice but to find them interesting. Either you pay attention to them and try to work with them, and maybe your system doesn't crash in the middle of the night and have like 1 million angry users banging on your door. So there's a bunch of ways we have of trying to deal with these concurrency bugs. Essentially, you can try to make your system run deterministically for analysis purposes, as in this isn't a practical thing necessarily to actually do because you're using concurrency for a reason. You have events, you have multiple users, something like that. But we have recording technologies that let you figure out, and for this exact moment, it was this interleaving of things that happened. So we can improve reproducibility. We can do all sorts of crazy monitoring. Just ask someone who actually works in like computer operations. They will talk about this for hours. We can try to shake up the implementation so that maybe we see the scenario under test instead of in the middle of the night. There's a bunch of stuff called linearizability checking, which is essentially where you record a bunch of operations from your system with like start and end markers, and you figure out, is there an interpretation of all these overlapping starts and ends that I actually like, as in this one legally happened first, and then this one, and then this one, and now we ended up in this state that I like. This is kind of linearizability checking, as opposed to there is no reasonable interpretation of these operations that ends me in a state that was like a permissible set of actions. Like you can have two things. It's like log in and hit delete user at the same time, and now your user is in some ghost state where it's still in the database, but it says it's deleted and you can't hit the button again. You know, all those messy, like, garbage scenarios. You're basically checking, can I always find a case where this was okay and an acceptable sequence of events? That's linearizability checking, and it will tell you, no, your thing doesn't do that. Here's a bug, fix it. And that's very helpful. And lastly, we have formal modeling, which is one of the more esoteric ones, really, where basically you come up with state machines, which you might remember from 121 and perhaps some other courses, which, you know, you have an initial state and then you go in different patterns and you have different transitions. And you basically model everything that's allowed to happen. And if you can then simulate this state machine, you can start analyzing. So for every combination of events up to depth 20 or whatever, do I see anything, any emergent behavior from my state transitions that I've modeled mathematically using set theory and for all and exists and all those lovely things? Do I see any emergent behavior that I didn't think was supposed to happen? Like you can write, you know, a few different properties that I will save for the demo in like one slide. Point is, you can do all these modeling things, and I'll be focusing on this modeling language called TLA+, which you all well knew, but the audience at the time didn't know that yet. And there's a bunch of other ones you can feel free to look up if you're curious and have eagle eyes. F-star, oh, that's the old name. It's called Rock now. Verus, Daphne, Promula, P, Alloy, they're all fascinating in their own ways for their own reasons. And unlike regular programming languages where you can do basically anything you want in any language if you try hard enough, these are specialized enough that you can't actually do anything in any one of them, and they are differently suited to different things. So, yay, as an expert, I get to learn all of them, and that's really fun because I love that. But that's an interesting and unique thing about these languages. Now, what is TLA+ anyway? The original presentation has one quick slide on this, and then I just blast through and talk about other stuff, but I'm actually going to go in depth on this so that you actually understand what I'm talking about. So basically, it's an abstract language. It has nothing to do with anything else unless you believe that it does. You have like a set of 1, 2, and 3, and then you come up with, those are actually the IDs of processes, and they are markers for this thing, and you have like an array of this stuff, and it gets transformed like this in each state, and it does whatever you believe that it does, but it does it self-consistently, and its analysis results, assuming you've related them to your system correctly, are real. In fact, I can code some for you right now. Here's a little demo module that is empty, and I'll show you some very simple things you can do. So first, I'm going to bring the concept of integers into scope, because otherwise it doesn't understand plus. Now it does. Then, what I'm going to do is I'm going to say we have a variable x. This is a state variable. It is a global variable. If you wanted lexical scope, it sort of has that sometimes, but abandon all hope, ye who enter here. It just has globals mostly. So now your state machine has one variable in every state that has, well, I didn't say what it has yet. And then, but now I can sort of start elaborating. It has an initial configuration which defines that x is equal to 1. Actually, let's be a little more interesting. X is in 1 and 2. So now we have two initial states where x is 1 and x is 2. And you can sort of have fun with this. Next, we write our next, interestingly enough. And we can define basically anything we want. In fact, we can say or. These are some very funny notations, by the way. I'm sort of skimming over them. You can just listen to my voice if the notation is unclear. But you can do and or, and exists, and if you've ever had to write like a term paper in LaTeX, or you happen to be doing research on the side, you may recognize a lot of these notations. That's not a coincidence. TLA+ was actually originally sort of specified by Leslie Lamport. And if you've ever written LaTeX, the La in LaTeX stands for Lamport. He made both of them, and he likes this notation. In any case, I'm going to keep this real simple and say x prime is equal to x plus 1. And that's kind of boring, Basically, we're just going to see 1, 2, 3, 4, 5, and your state space is just an infinite linked list going off into infinity. And that's kind of where I'm going to keep it here, there, but I'm going to show you what's actually interesting about this, because you can specify this. Good job, you can run it and it will generate an infinite state space. That's like super unhelpful. However, you can also state facts, like x does not reach 5. And this is just a naming scheme, right? What matters is I'm saying x is less than 5 here. So I've just called it x does not reach 5 because I like relatively readable names. And now I'm going to claim x is less than 5. And it's now going to be able to check in every state that it reaches, is this true or not? Do I find any counterexamples? And you might think with your human brain, oh, well, I can find one for you very easily. That is correct. So can it. And it found an error. That's nice. Invariant x does not reach 5 is violated. And it will show us a nice little thing where, oh no, the display is a little corrupted because this is so tiny. Please work. God damn it. All right, let me just close everything. Oh yeah, there we go. Here are the values. So here it picked x starting at 2. I let it pick 1 or 2, and it just picked one of them. It would have calculated the other one if it didn't find something interesting already. Start x is 2, 3, 4, 5. Well, that's not less than 5. There's your counterexample. And you can write arbitrarily complex, arbitrarily specific things where some crazy cross product may, in some cases, reach some random edge case you didn't think of, and it will just crunch through all the combinations and tell you. Completely deterministic. Not the most efficient process, but on modern machines you can go into a few millions without too much trouble for combinations, and that's what it's good for. It will surprise you. Yes?
Why did the other condition start with the and, but the x doesn't reach 5? It's just straight equals.
I closed the source code. Let me find it again. Sorry. I can answer this pretty simply, is it doesn't really matter. It turns out a single and just writing it is the same.
Okay, so we didn't need to do it.
Yeah, sorry. I probably, for understandability, should have just skipped the and part because it doesn't add anything. But no. It's just I'm just saying, like, pedagogically, that might have been a good idea. I've seen too many lesson reviews. But yes, that's a good question. And if you wanted to add more, it's like software engineering easier to now add more rather than having to edit the first line. But ultimately, none of this matters. So, cool, thank you. And feel free to interject questions. I am largely ad-libbing most of this, so I'm happy to sort of digress and move around as and when. In any case, that was my little demo. Hopefully now you understand a bit more what TLA Plus is capable, despite my example being perhaps a little basic. But you can just keep building on this. You can add more variables. You can have lists, sets, dictionaries, lists of dictionaries of sets of whatever with for alls and exists and quantifications. And you can start talking about temporal sequences, like once this has happened, this may then never happen or must always happen, and all sorts of fun stuff. It's Leslie Lamport's life work as a theorist, basically brought to life as a programmable thing, despite his insistence that it would never work and it was not a thing, and then someone did it and he was like, oh, that's actually really cool, and then now it's a thing. Anyway, so that's basically what TLA Plus is. Now, what the heck is OmniLink, and why is that the title of this slide deck? Well, you've got this problem, right, where if I believe that my TLA Plus represents what my, 10,000 lines of C++ actually does, because, apps are not this small, apps are not this theoretically sort of simplified, and even if you write an elaborate specification, you're hitting like 200 lines of TLA Plus. That is still tiny, because if you write more than that, you start running into billions of states, and that's just not workable, even with modern machines. To be clear, there are other technologies that can do this other ways, and there's a bunch of pros and cons. But ultimately, if you have a simplified, abstractified language like TLA+, you start asking yourself this question of, am I really sure that I actually implemented what I modeled mathematically? And you might find yourself asking that question. And several people have asked this question. sort of dating back roughly 5-6 years. So some of them are us. That little tracelink side, that's actually a previous work that I co-wrote with my supervisor. I won't get into details, but these are all uniquely interesting. Some of them are big commercial deployments, like the Confidential Consortium Framework. That's, for those of you who happen to randomly know what that is, that's an obscure Microsoft research project. Well, obscure relative to sort of big headlines. It's actually quite successful and quite popular in its own niche. There's Converos, where some folks at University of Nanjing were doing some interesting things, modeling kernel spin locks and stuff like that. And ultimately, all of these things are to do with logging what happened and figuring out if this model that we have actually matches what we logged. And also, there's a bunch of other stuff on an aside I won't bring up too much, called model-based testing, where you can take your TLA Plus and try to generate a test suite out of it, which is, again, a deterministic generation process where you look at what the model says in its like graph. It's a directed acyclic graph of states, by the way, just that's what it is as a data structure. You can navigate that and try to figure out paths through it that are interesting test cases, and some folks that I know have also done that. Yes? I believe Tony has a copy and will,
about
yeah.
11 o'clock this morning, so
Woo!
10:30 or something, so I will post them.
Yes, and you're definitely welcome to them.
They're good for printing out and putting under the bottom of the birdcage.
Mm-hmm. Yes. Anyway, back on topic. Essentially, you have this idea of trying to match up the implementation with the TLA Plus behaviors. However, the position of my research here is that all of this existing work uses logs in a sort of line-by-line format like you would normally expect. Like normal logs say, this happened, this happened, this happened. They have like little timestamps and maybe a little bit of metadata about what happened. And that's what a normal log looks like. But you have kind of a problem, because if you say increment x, and then you log I incremented x, just keeping with our previous example that's still up there, your log and the increment are out of sync. The log can end up timestamped after someone else also incremented x, or like someone looked at x and saw it after the increment, and then you logged that you incremented it after they logged that they saw the increment. Like there's this strange desync that can happen, and there's a bunch of fundamental limitations in how you can log things, because it's like a little out of sync no matter what you do. You can log it before you do it, and you're still wrong because now it just desyncs the other way. My insight essentially is, what if I log both before and after and box it in? Like I log it too early and I log it too late, and now I know it happened somewhere in there for sure. If I logged it only early, it can happen arbitrarily later. If I logged it only too late, it can happen arbitrarily earlier. But if I log it in between, I basically end up with these boxes of time. And that's what we're really getting at here. Now let's see if I talked ahead of my slides or not. Only sort of. So essentially, what we're basically proposing here is linearizability checking is actually this idea of, remember how I mentioned briefly earlier, it's about these starts and ends, and is there a reasonable interpretation of what order these things that start and end in overlapping patterns happened in? Is there an interpretation that makes sense? That is literally what I am asking. It turns out it's a whole established field of analysis that I sort of accidentally reinvented in TLA+, and now my proposal is in integration. We have trace validation, which is a known technique you can do, but it has this problem of before and after, making it kind of worse than linearization. And you have this kind of model-based testing, where I'm leveraging knowledge about the structure of the TLA+ to produce testing harnesses. I'm not doing this in a very intelligent way, mind you. I'm just saying, look, our TLA+ looks like this. It has an API functionally that is these events. For example, next here just means, yeah, it incremented. So I can log next at various points, and this will imply that's where it incremented. In fact, I can log time boxes marked with next, and that's a thing. But conversely, if I have an implementation of an incrementer thing, which again is not very interesting, but imagine it's a more interesting API call to some actual system, then my test rig should randomly choose across multiple threads to do increment. And if I had 2 operations here, it should do like those 2 and stuff like that. So we're using the model to inform how we build our test rigs. And those are the 3 things we're really doing for OmniLink. And I guess this is a diagram for what I was gesticulating earlier, where you have different actions, and they have starts and ends. Time is going left to right here. And this is an ancient idea. It dates back to, did I put this on the slide? I think it was like 1990-something was when someone originally published this concept. And people have been working on it for like the last 20 plus, however long ago that was, years. And all of this together ends us up with this type of design. This is what OmniLink basically is. And this is where I get into what our research is and, how it works and stuff like that. Feel free to interrupt me. Feel free to sidetrack me. In some sense, I've given you the high-level overview of what all of this stuff is as of now. And now I'm just giving you illustrations of how it applies, what research looks like, all that stuff. So at this point, I'm willing to draw a line and say, even if we don't finish these slides, this is okay. But if I just keep going and we finish them, that's fine too. Just anyway. So we have an API fuzzer that you just build, you just write code. It's like you write a main loop that spawns a bunch of threads. Each thread does like some number of operations randomly. And then you join the threads and you had logging on all of those operations. That's literally it. It's like 100 lines of C code or whatever. We have a database of all those traces that we get out of that logger. We have like a format that we use. The old version of OmniLink that these slides is technically talking about has these in message pack, if you know that standard. We changed to CBOR, which is like JSON's melted binary cousin, for various technical reasons that I will spare you right now. But in any case, it's basically a bunch of binary serialized structure that looks an awful lot like JSON, except the map keys don't have to be strings. Then we have the TLC model checker, which is commonly used, relatively venerable tool from dates back 30 years or something to back when Java didn't have generic types. Imagine that. But it's still maintained. I've given it a pull request or 2 every now and then. When I ran that thing in VS Code, that was TLC spinning up in the background. You can use it to check these puzzles if you generate the right TLA plus around it. And then we need to be able to look at the counterexamples, because when it says no, you need to understand why. And even just that example where it's like, this is a path which didn't work, that's actually insufficient in our case, and I will explain why. I immediately regret not going to this slide earlier, but that's basically everything that I said with annotations. Feel free to look at that on the copy of the slides later. Breaking this down a little bit further, we're actually using a tool called RR to do sort of chaotic thread scheduling on the fuzzer side. So, you write the normal, boring sort of, spawn a bunch of threads, do the things, and that's fine, but that's not really going to find you the edge cases. Because if you run it repeatedly on a normal test machine, that doesn't simulate load properly, it's going to do roughly the same thing each time. However, we have a bunch of lovely technology that lets us force programs into strange threading configurations. And I definitely encourage any one of you who is going to write threaded C, C++ at any scale to check out rrproject.org. It's a really interesting open source tool that started at Mozilla back in the day and is now still open source, and it still works. What's interesting about it is it will record your entire program's behavior down to what came out of malloc. So you know how when you allocate memory, every time you debug your program, the address comes out different because of random underlying behaviors? Under RR, you can actually see the same thing happen over and over again, and all your nanosecond system timers give the same numbers every time, all your memory addresses are the same, every single piece of your program is perfectly determinized using a fascinating system that they show in their white paper. I read about it and I was like, wow. So if you want a fun read, go read their white paper on their website. It's really cool. Anyway, this is mostly me getting a little off track, but I feel that's interesting, and some of you may genuinely save yourselves some artificial hair pulling out, hair loss at various points by using this tool at certain points in some of your potential careers. Yes?
What was the name of the domain?
RR, literally the letter R twice, dash project, normal spelling.org. Yeah, absolutely, check it out. I may have forgotten to link it in the slides, but feel free to ask. It is findable. Yes?
Wait, how common is it for like engineers to write that incorrectly?
I would say there are between hundreds and thousands of people who know how to do it worldwide, and that's both a lot and really not that many if you consider the actual number of software developers. Yes?
Yeah, because my question is, like, my understanding is the purpose of this is to test if the invariant holds, right? But I'm
Yes.
wondering, like, how often is it that they get the invariant wrong?
Oh, sorry.
So that your,
Yeah.
like, the open source project you built will still function properly, but then the basis is just wrong.
You mean as in you are mistaken about what the invariant is?
Yeah.
That is decently common. In fact, that's an important thing to be aware of for the whole OmniLink project. It tells you that there is a mismatch, but not why. Is it because you modeled the system wrong? It might not even be the invariant. It might be an entire model that is wrong. Or your system has a bug, and it's up to you to make a human judgment call and say, well, which one of these do I believe? Which one of these looks right? Should this have been possible, or does this make no sense? You could have also even logged it incorrectly, and both your system and your model and your invariants are all correct, but because of your logging coming out wrong, it looks wrong to the thing, and therefore it says it's wrong even though it's not wrong. Every single one of these can happen. It gets a little mind-bending, but that's the tool.
Like, doesn't logging add a lot of overhead? And does it like cause any? Like, it wouldn't have happened if you didn't log it.
Right, so you're right, and there's some interesting nuance to why you're right and how. So, to be clear, I'm not describing this system as suitable for online system monitoring. That's a thing you can do, and I did mention it in one of the slides, but it's more other people do that. We actually don't do that. We do this under test, and as a result, one line of the sort of overhead thing is not really considered important. But that doesn't answer your question, it's just context. Secondly, if we have logging, this will change timing behavior, and this may cause bugs to appear and disappear. By some logic, yes, this perturbs the system. However, I would suggest that your system should be resilient to any and all of these timing differences anyway, but without the RR fuzzer, like chaos executor, you would be seeing, like, in production or like under test, you would see one set of things, and then with the logs you'd see maybe a different set of things. But if you're using chaos execution, which forces all the threading like interleavings to be a mess anyway, you basically run it all through a blender, and I can't entirely tell apart with log perturbation versus without, because you've perturbed it so badly using the chaos testing tool that it may not matter. However, you are still correct, but that is some interesting nuance to you being correct. Does that? Yeah? Because otherwise, yeah, logging things super cleanly and actually capturing the true executions. There's a guy I believe called like Ali Meruz, or I hope I'm not misremembering his name, but he's actually at University of Waterloo, and about 6 years ago he published a project on extremely low overhead logging where you can run true multi-threaded workloads. Keep in mind, RR actually forces you to run on one thread and just messes with the scheduler, whereas this is true multi-core workloads with like tiny overheads, and he's like the only person who ever did that correctly. It is stupidly hard. But check out his research paper if you're interested in that. I obviously didn't give you enough information to find it, but
I think
yeah?
I went to like a career talk a while ago, and they were talking about something called like magic trace.
Okay, I haven't heard that term. Can you describe it a little bit more?
I'm not sure if I can describe it that well, but they use something like specific to the Intel processor, and they look at the
go
somehow
on.
they track the branching very low level, and that gives you the exact execution. Of, like I can't describe it better than that.
Yeah, this sounds like a thing you could do. It's a little bit adjacent to my expertise, so I also can't comment on it very much. But I would say the distinction here is, in a way, because we're comparing against such a vague mathematical model, most of that branching information doesn't really matter as long as you can exfiltrate basic facts as like what the number was that went in the function call. So it's likely only sort of relevant, but likely also related to the thing I just said about that guy from Waterloo who did something similar. Feel free to look into this. Like, you have opened one rabbit hole of this research area that I've actually not explored, but many people have, and it's fascinating. Oh, a hand, yes.
Sorry, what was the name of the property?
What was the name of which one? Sorry?
The one you've been pronouncing.
Oh, I genuinely cannot remember. Like, I know how to find it if you ask me when I'm at my computer properly and I have a minute. So just the simplest answer is, if enough people want to know, I'll tell Tony and he can tell everyone. And if just a couple of you want to know, email me. You can just Google me, fackett.com is my email address is on there. You can literally just email me and I will tell you after I look it up for 5 minutes. I'm sorry I don't know it off the top of my head. I think it's Ali Mehruz, where it would be Merhaouz. However, I might even be saying the wrong faculty name. I just know it's someone there, and I might be saying the name of the person in the lab next door or something. So just ask me later, and I will tell you. And I know Ali Mehruz is a real faculty at University of Waterloo. It just might not be that one. But thank you. Any other thoughts? All right, let's keep going just a little bit more. Generally speaking, these are all the definitions we have. We have various interfaces and things inside the TLC model checker. Just in terms of defining things, we have to define what time box overlap looks like, and we have a TLA plus condition for that. And then we also have where you are in the log, where we have it's basically, we're misusing the concept of a vector clock. If you've encountered that, I believe that is actually on your syllabus. So we're not using it correctly, and some of the properties are different, but it looks like a vector clock, if you're wondering. Oh, right. And the part that the user actually has to write are these ones. So you have to write some of the API glue. You have to come up with a bunch of massaging to make TLC not go into the billions of states, because that can happen. And you also have to express what your system should be doing in TLA+. Everything else just is implemented in OmniLink, and you can just use it. So I guess I'll just start going into a running example of what this looks like on a more realistic case. And this, I believe we have a version of something like this in our open source project. However, this is not published work yet, and we're still kind of working on it, so subject to some change. I've actually been rewriting the project a lot. In any case, the example stands and the theory holds, so let's have a look at it. We have one variable, which is q, and you can enq, so you say enq element, and that means the next version of the q is the old q with the element appended to it. This is all done using immutable data structures and kind of mathematical formalisms, so that's if the syntax looks strange or it seems to never really do any mutations, that's why. Then you can deq an element, and that means the q must not be empty, because if it is empty, you definitely didn't deq that element. And if the q isn't empty, then the head of the q must be equal to that element. You might find it interesting, for example, that we're deciding kind of a priori what the element was that we deq'd before we deq'd it. You are correct, we are doing that. What's interesting here is we can just say there exists some element such that this predicate is true, and now we're letting the predicate decide the element. technically what the model checker is doing is iterating over all the values we know of, and you should pick a small set, otherwise you are going to spend a while doing this. And for every one of those values, we check that the queue is not empty and whether that value is at the head. And as a result, it will pick the correct one if there is one. That's kind of operationally what it's doing, but this is a mathematical statement, and there are interpretations of this where you can sort of set element, you can just leave it kind of blank using exists. It's kind of weird, but that's kind of an interesting thing about TLA plus modeling. That's why I want to highlight that. And essentially, if those two conditions are true, again, it has like this short-circuiting AND evaluation. If you're used to writing A and B and C, and A is like a null check, yes, it is exactly that. That is exactly what is happening. Then you just say the next queue is the tail of the queue, because we just throw out the element, we know what it was, and we dequeued it. Then you have our good old init, which just says q is equal to an empty. These are called tuples mathematically, and they have this funny syntax, but it's a list. And then we have this exists, where we will check every next state that you can have is enqueue or dequeue of some element for any element that we care about. And that's how you step forwards in the state machine. Again, this has infinite states, technically. Your queue can grow infinitely. And if your queue is very long, every single state contains a copy of your queue. And that's a real quick way to make TLC give you nothing interesting and spend a very long time computing a bunch of lists. So for instance, when I say model checking heuristics, what I mean is, by the way, just don't consider queues longer than 10. Just give up. They're not very interesting, and I just claim this is not important. If I get my heuristics wrong, this can mess up my results. This is just a thing that you run into. Most systems require some degree of massaging. Some of them can compute like for alls and exists much more precisely using more advanced puzzle-solving techniques. TLC is not that smart, but this is the type of thing you get into if you start dealing with formal specifications and stuff. And I suppose I should shamelessly plug that I am by no means the only person working in this type of area at UBC. If you think, oh, that's fun, let me learn more about that. Check out the Software Practices Lab. They have a bunch of excellent researchers working on all sorts of crazy like analysis of Rust code and stuff like that. And it's all like this. And if you like that kind of stuff, it's all very interesting. Anyway, back to our example. That is our specification, more or less. And also, that little next thing, I am literally reading enqueue-lm, dequeue-lm as our API spec. And therefore, when we're writing our fuzzer, you have to implement enqueue with where it has some lm, and dequeue where it has some lm. And in logging, you can basically choose. Do I pick the lm and then call the API with it, or does the API return the element? It does not matter. I just get it out of the return value, or I pick it and record what I sent in. All of these are okay. You can just log them as is, and you get a time box with the correct data, and it is now solvable with relation to TLA+. I'm just going to skip that slide and maybe just point out that I accidentally said this slide early. So, for example, when you're doing enqueue, you choose the random element, note your start time, call the API, note your end time, then call record. And when you're dequeuing, you just say start time, you call dequeue because it chooses what comes out, then you end time, and then you record what came out. So just either one is fine. It just works, basically. You can deal with the mismatch between the mathematics and how code control flow works just with a little bit of like 2 lines of code, basically. And I am now going to skip all of this because I went on about it for like 10 minutes already. Now let's look into how you can solve all of these types of puzzles with a model checker. For instance, you might have recorded something like this. You will enqueue 1 and enqueue 2, and those are overlapping operations, so we're not really sure which way around they're supposed to have legally happened. Then you enqueue 3 also, but that's definitely after the first 2. You can visually see that the time boxes are separated. Then you can dequeue 3. And if you're thinking really, really fast, you might realize there's something strange about that. Does anyone reckon, is this supposed to work to begin with? Can anyone suggest? I saw your hand first somehow.
The DQ is being called before the OnQ, and so if we are going by linear time, it's kind of weird that we're trying to DQ the element 3 before we've OnQ'd it, and thread 3 shouldn't know about the element 3.
Right. That's an interesting take, actually. And I should mention something interesting about linearizability, because that's actually getting into something that's kind of fascinating. This doesn't mean we've decided that we're DQing 3 yet. It merely means we started calling the API. Our thread can freeze here, we get scheduled to everything else in the world, and then the actual API call could have run here. So, in a sense, legally, there's nothing wrong with technically knowing about 3. The problem is much simpler, actually. Can anyone spot what's wrong with DQing from a queue 3? When did we DQ the other ones, right? So, let me just show you this as kind of a diagram. Like, this is one linearization you can pick, and essentially, like you were saying, or like you were getting at, rather, it's important to understand which before and after matters. Like, when you make an API call, that doesn't mean it's happened yet. In fact, until it is entirely returned, if it's operating on multi-threaded data, it is performing some incomprehensible arbitrary interaction across multiple threads potentially, with like locks only being taken in some cases, events being delayed and moved around. And if you ever want to look into weak memory research, that is a real thing your CPUs on every single one of your machines is doing right now, that no one ever pays attention to, but is a fascinating rabbit hole if you're curious. And mostly, I would shout out Yanhao Wei, who's a relatively new faculty here who works, specializes on these bizarre memory effects and data structures and things where it's like, actually, you don't need to lock that. You can just do this other crazy algorithm, and I have 5 pages of math proofs about why this is a thing. And then I write it, and it actually works, and it has high performance, and it's interesting. And that's like his thing. He's interesting. He's actually co-authored on this work because this analysis technique helps him figure out if his code works or not. In any case, I'm going to skip that and take us to this lovely diagram, which tells us the kinds of reasoning that we can do with OmniLink. For instance, and I'm sorry, some slide transitions got lost in the conversion to PDF. That is my bad. Start with Q empty. In Q1, Q now notionally has 1. In Q2, Q now has 1 and 2. In Q3, Q now has 1, 2, 3. DQ3, that doesn't work because the head of the queue isn't 3, it's 1. Next, well, we can backtrack and make another choice in our decision tree. Try to DQ3 before we enqueued 3. Obviously that won't work, but TLC doesn't care, it's just enumerating things. It turns out that also doesn't work for the simple reason that it's still, the head of the queue is still 1. And you can go back and say, well, actually, we could have enqueued 2 and 1 the other way around. Now the head is 2, so it still doesn't work. And you can also say, well, what if I enqueued 3 after doing all of that? Does that? Nah, it still doesn't work. Now you just still have a head of 2 because we forgot to log dequeuing 1 and 2 in any order. That would have made this at least more possible, but it's just not possible. And I'm going to elect to skip this slide. It's an interesting detail, but it's just kind of an extra feature of OmniLink where you can split things into substeps. Let's just ignore that part. In fact, let's just go a little bit further along. And note that to interpret all of this nonsense, you had a diagram in the slides here, but what about how to actually use the tool? Does that, how do you understand what happened? How do you try to reason about like these graphs and these enumerations that were performed and what the search process, right? How do you reason about that? And if you happened to already be TLA Plus experts, you might realize that TLC gives you one counterexample, which when you're searching from the beginning of the state space, fanning out, is nice because it typically gives you a really short counterexample that summarizes what's wrong with your system. However, if you're trying to find any combination that satisfies this kind of consumption of the trace, what you actually want is every longest path, especially if there's many of them, and why they didn't work, which is completely impossible with normal TLA plus tooling. So I built one. And unfortunately, this doesn't match the demo, but I can show you our app. And I'm actually in the process of rewriting this. This is in glorious JavaFX. Those who know what that is. I built it in JavaFX because the only library that can read the trace files that I have is in Java, and well, it's in Scala actually, but it runs on the JVM. And as a result, it seemed the simplest way was to build it like this. It took me 2 days. I'm very proud of it taking 2 days. Everyone looked at me like I'd be gone for a month. I came back 2 days later with an app that sort of worked. It's a little janky. It lags sometimes. I know why. It has architectural problems. But it works. And it kept the research going, and we hit our paper submission deadline. Take that. And now I'm rewriting it using like some web technology and like a SQLite database and stuff. And there's a very long list of reasons why, which I will spare you. However, we can now look at some counterexamples. This is actually from an ongoing thing, and we're not quite sure why this fails yet. But the information we have available to us is stuff like this. So here we are at the end of an analysis tail, like we're at the tail of it at element 407 of a sequence. And our insight is we don't need to really view the other like 300 sequences, 400 elements. Like they usually don't matter that much. We just want to step backwards piece by piece from there. And that's much easier to render than rendering the useless initial state and like 407 useless states, and then, oh, eventually maybe you'll scroll if the UI doesn't overload. Not a thing. Do not do that. It does not work. You'll crash your VS Code. Trust me, I did multiple times. Essentially, you can see what your action was. It had this start point, this end point. Those are real timestamps you can use to access the RR debugger view. Here we have our funny little vector clock, where it turns out thread 0 made it to 102 steps, 1, 2, and 3 also 102 steps, and thread 4 hit 3 steps, apparently. That's very symmetrical, I'm surprised. But it turns out that's what happened. Here's what it was trying to do but couldn't, which was apparently dequeue with token, and we were dequeuing elements 52 and 57. I have kind of a diff view. Again, this is janky and bad UI design, but plus means added, tilde means just sort of changed, and exclamation mark means it's gone now. This helps sometimes, but is maybe just confusing here. Again, this took me about 2 days to initially build, 3 days to rebuild one time because it was not good. So I spent 5 days on this, and it's already like kind of usable. I'm still proud of that. But again, let's not mistake that for actually good design. And here are the various state variables. You can just see all the different queues, 52 and 57. And I can observe, for example, that we were trying to dequeue, what does it say? 52 and 57. And it has 50... What? This is a good example, actually, of what it's like to read these things. I cannot immediately tell you what's wrong with that and why the 52 and the 57 are seemingly there correctly, but also it got stuck. I suspect it's something to do with the time ranges or some malfunction of the tool. And now I would have to go into a long investigation, which ultimately led me to have to rebuild this tool. So I'm doing that now, and we'll eventually figure out what's wrong with this. The point is, however, that's what the viewer looks like, and we can build this. And as a research point, that's a good start, and I'm continuing the investigation and its ongoing work, right? Point is, if you want to debug it, you just have to investigate and take it apart and figure out what the heck happened. And who knows, sometimes even the tool itself is wrong. And I couldn't tell you it's not the case, but I'm not really sure. Anyway, I'm just going to skip the screenshots that I included because I didn't have a demo here originally. Oh, it'll also show you various time ranges and stuff if you want. I can actually just click this. Never mind. Like I said, I'm rebuilding this app for a reason. And yeah, so that's basically... Oh yeah, and this is how you can get the debugger to get into that state so you can see what the code actually did, not just this weird logical representation that is, I admit, on its own kind of confusing. And that's basically all I have to say about the design. I get the impression our time slot is still... Like, this is an hour-and-a-half time slot, right?
So you've got 25, 30 minutes.
Okay, well, that's great. I have plenty of material. But I should sort of pause here and sip my tea for a moment and ask if anyone has any questions about the design or anything I said, because I'm about to sort of segue into research results, which might also be interesting, but for completely unrelated reasons. So, yeah, any thoughts? Yes?
Do you know of any examples of TLA Plus being applied and what kind of projects they've had?
Well, this one. Yeah, sorry. Okay, there's different levels of this. So actually, part of this project was an industry collaboration with MongoDB, and we actually worked on their storage engine as part of this, and we found some interesting stuff. However, that's just us this time, this one case. Stepping back a bit, what about TLA Plus's adoption more generally? I will point out most of these verification tools are adopted by, like, maybe you are wildly successful if 3 teams use your product somewhere. TLA Plus is kind of a funny one. I anecdotally, and I'm not allowed to tell you how I know this, but apparently it was used to validate sales procedures at Nike shops. Like the little iPads that the shop attendants have to, like, manage your Air Jordans purchase or whatever Nike sells. I don't actually know. But the point is, all those things about, oh yeah, and then the customer walks away in the middle, and then you have to, like, cancel the sale, or, like, they didn't give you a coupon card, or I don't know, whatever Nike sales attendants do. They basically modeled all of that, and it helped find edge cases in their sales procedure. So that's the most odd example that I've seen, but I have legit seen a Nike representative at an undisclosed, non-publicized description of this being a thing. They are very tight-lipped about it. Meanwhile, there's a few teams at Microsoft that have built TLA Plus models and used them to proof their designs. Usually what happens is not so much you find bugs that ever made it to code. Like, you'll just be like, oh yeah, your whiteboarding session found these 6 issues, and thus we will not implement it wrong in the first place. That's a common usage that dates back like 20 plus years. Older uses of TLA Plus include cache coherency protocols on some older CPU models that I believe Intel, I think there was some, like the source code actually has copyright from like Qualcomm or something like that. Anyway, it sort of kicks around in various places. There's a few teams here, a few teams there. That's what I said, like there's hundreds or maybe thousands of devs that use it, and they all have these funny little bugs that they use. Nothing high profile, nothing probably that hit the headlines. I have notably used it to fix errors in the documentation of Azure Cosmos DB, for example. They paid me to go do that for a few months. That was interesting. That wasn't even the code. That was just the docs are objectively wrong, and I can prove it because they have this edge case if you take it literally. And then I asked the dev, and the dev told me, what are you talking about? It doesn't do that. And we went through that process, and I pull requested their documentation, and eventually they accepted it once I said I was publishing a research paper on how it's wrong. So that was interesting. Yeah, the list goes on, and some of it occasionally has me in the corner doing something, and a lot of it doesn't because it predates me by many decades, any of my research career. Does that sort of answer your question, maybe? Cool, thank you. I appreciate the story time opportunity anyway. Any other thoughts or questions? I realize I jumped into the slides, but we were still here basically. All right, let's just get into it. Speaking of which, what were we doing anyway? So you have this evaluation process that goes kind of like this, and Brian somewhat knows about this because he's doing that on another experiment right now. So you write a TLA plus specification if you don't have one. You rarely have one, but occasionally, for example, MongoDB has like hired, I swear, 5% of the TLA plus community, so like 6 people. But you know, that's good, right? And they have a bunch of TLA plus specifications, and I came in and I used one of them as the basis for this experiment that is on the next couple slides. That said, otherwise you just sit down and write it yourself. I've written a few of them, and Omnilink actually really helps because you're having to reverse engineer an existing project. So you're like, all right, I think it works like this. And if I couldn't check that, I would just be unquestioned and wrong. However, I test it, and it's like immediate failure. Oh, god damn it. All right, okay, what is it actually doing? And then we go through. Is it documented incorrectly? Is it just not doing what it's supposed to? Am I just wrong? Many of these things can happen in many combinations. And that's what we're dealing with concurrent queue, for example. Like this thing here. I'm figuring this out because this is a decently documented GitHub project called Cameron314/concurrent queue with like 20k stars on GitHub, and we thought it would be interesting as a quick introductory thing to have one of our interns try. Yeah, so it turned out to be one of the most complex problems we tackled precisely because it has crazy data consistency guarantees that are extremely precise and very weird. So it's a queue, technically, but some of the time the elements are allowed to come out the wrong way round, but only sometimes, under some conditions, and we're still figuring out exactly what that is. And it's basically got this whole performance chunking thing, and basically within a chunk from the same sender, it stays the same way around, we think, we hope, but between chunks, between senders, the things can get swapped around because it doesn't hold any locks in certain cases. And we don't understand that, and we're working on it. But that's an example of the hardest TLA plus authorship case we've had, and we're still dealing with it. Very interesting, though, and if we do get this even somewhat right, like this is more documentation than this project has ever had, period, because all we have is test cases and prose, which is great, right? That's actually really good. Sometimes you're missing most of the prose. Sometimes the thing has no test cases. But, you know, this is a diligent open source contributor who's been, you know, hammering away on this project for years, and it's got some adoption. But hey, we can add a lot more to it. So that's fun. Then we got the fuzzer template, like I said, and you fuzz the system, and in this case I tend to go for like 500,000 operations, so which is basically 5 threads with 100,000 operations each. I would want to stop at 10,000 because that takes less time, but 500,000 is only about 20 seconds of runtime, and it finds so many more issues. Like there are cases where I will not realize our spec is wrong until I run it for like 10 times more time, despite using the chaos fuzzer. So that's a reality of using this tool. And then as and when you find all sorts of issues, as I have never shut up about this entire presentation, you have to go back and fix whatever it was and keep working until stuff happens. And yeah, it's great for work in progress TLA+. The main thing we used it for that's like the famous industry system is if you've looked at the internals of MongoDB, you will find that its data store is a thing called WiredTiger, which incidentally was written by the department co-head's husband. Like actually, he sold it to MongoDB like 10 years ago. He's a guy called Keith, who's also notable for like various contributions to computer science. But yeah. In any case, it's still there at MongoDB being used, and people wanted to test its correctness because it's a bunch of really, really tricky C code. Like when I presented this, we actually had a different faculty member from ECE, Sasha Fedorova, who came up to us and said she'd been pulling her hair out over like this concurrency bug for 3 months straight, and she was looking to see if we could investigate it or reproduce it more easily in OmniLink. We tried and kind of ran out of time budget for the project, but it was very promising in some strange ways. Like basically they have paragraphs of prose documentation in their C code, and it would be quite interesting to transcribe that into a little state machine to track this one piece of the project. Like this is by no means the entire code base, like not even close. But they have like this tree structure, and the tree structure has this little thing, this little integer field in it. And the integer field is sometimes a lock, sometimes a marker of whether a page is in memory. There's a bunch of other crazy sequences, and there are cases where it'll flip-flop between these two things as pages gets loaded and unloaded. And oh, by the way, this thing is being hammered on by multiple threads, some of which use atomic operations and some of which don't. Oh my god, right? So it'd be really interesting to get a bit more clarity on that, get a model of it. That'd be great. And maybe one day I'll get back to it. But till then, that's an open question and evidence of, you know, the kind of insanity that happens inside these kind of projects, which is by no means unusual. That's just what it's like to code a big project with lots of complicated concurrency and C code and stuff like that. I guess other than that, I should basically say there were a bunch of challenges in terms of the model being quite large and ambiguous and not built for OmniLink. I had to sort of tweak it in various ways, which I managed to cross-validate using the verification tooling, which I thought was pretty neat. It basically had this thing where it remembered every transaction and made TLC note them all down, which is like, that's good mathematically. You have a function from transaction ID to transaction. That's great. Except that if you do not need, except that if you're trying to follow a single path through like 1,000 transactions, remembering all of them may put a lot of stress on TLC and waste a lot of memory and time, which it absolutely did. It capped out at about 1,000, I think, total operations before it became unworkable. So I basically made a second version of the spec that conveniently forgot transaction IDs in a pattern so that it would not consume too much memory, cross-validated it both ways with the original thing to prove that the only difference was technically you could reuse a transaction ID without getting punished for it, but I will take that in exchange for being able to run the full 500,000 runs, which it now can. So that was a bunch of stuff that happened with WiredTiger, and we found some funny issues. So some of these issues are just our fuzzer being very unintelligent and very impolite. So for example, if you get told, your transaction failed, roll back please, and my fuzzer's just like flips a coin, nah, I'm committing. It turns out if you say commit like twice in a row after it tells you to roll back, it just sort of starts saying yes, which was odd, so we put an issue for that. And there's this really strange scenario where if you have a write conflict, which basically means two things tried to write to the same cell of the database, and one of them got backed off because they're concurrent transactions and they're allowed to do that. Also, Tony, in the background, if you want to, apparently this isn't plugged in, actually. Anyway, that's a very strange thing, and its investigation is ongoing. They actually got back to me 6 months after I left the internship and asked me for more documentation, and I haven't heard from it since. But it's amazing they even got back to me. Like, the normal pattern for this is, that's a nice issue you have there, backlog, never heard from again. So I love that they even bothered replying once. That was really cool. And maybe they'll get to it. You know, it seems they're quite diligent. And maybe eventually they, who have more expertise in their code base by far than me, may eventually figure it out with the info I gave them. That's nice. Some other just fun little details of this TLA Plus specification has been used for a lot of validation stuff. They actually used it for a generative like model-based testing thing. You know when I said model-based testing right like 45 minutes ago? Yeah, one of those projects was actually by the authors of that specification, who are Will Schultz and Murat Demirbaş, who are researchers at MongoDB and some of that 5% of the TLA Plus community. And I found, when comparing the other way, that they had slightly over-constrained some things. These are very minor details, but it's interesting that we can catch these. For example, if you have two transactions on the database that touch the same key, with the same little timestamp thing, which is a complex topic that I only half understand about how MongoDB manages the concept of time, they can just do that with the same timestamp. And in the database, and in the TLA plus, they had like a less than condition, and it was supposed to be less than or equal to. Little things. Also, apparently, there's this assumption that transactions work in some kind of order timestamp-wise, which is debatably true if you read the actual documentation of WiredTiger. So that was a funny thing to find and have to work around to some extent. That actually relates to the two conflicting writes thing, where the timestamps are kind of like in a funny order they don't expect. And that's likely why the system both works in production in MongoDB today and has this strange latent issue that may be interesting. Unclear, right? Sometimes you find something and it's like, this affects no one. Oh, well, I mean, I guess now we know. All right. But yeah, that's the WiredTiger story. I guess any questions about the WiredTiger story? I've already added a bunch of like flavor text and stuff. But any thoughts on that, or should I just move on? Well, I got to have a sip of my tea anyway. All right, let's see. So this is now a completely different application of OmniLink, balanced augmented trees. You know, when I was shouting out Yuanhao Wei and his work, this is that. So they actually got accepted to, I don't remember what the acronym is, but it's PPOPP 2026. And they basically constructed these data structures which have this very advanced concurrency control mechanism, which involves using a thing called a chromatic tree or something that is then reflected in an immutable copy. And the upshot of all of this is, you know, normally if you have like Java concurrent map, if you've used that, or basically any dictionary that supports concurrent accesses, you can access a key. You can read it, you can write it, you can usually do like a read, modify, write operation. But if you want to access like a range of keys all at once, you have no guarantees that's going to come out like as if it happened in one atomic operation. Well, these trees do. You can actually say, range check how many things are in this range, and it will correctly tell you, despite being a concurrent map, and your operation being concurrent with arbitrary reads, writes, inserts, deletes, and everything. It is a crazy technique. They have these really advanced like research tier work on how they've done it. And we wanted to go in there and see if we could find bugs in it, both bugs that they knew about as a test for OmniLink, and any bugs they didn't know about, which would be great to know. And also, there was no TLA plus here, but it's literally a dictionary. It's easier to write in TLA plus than in normal code by a mile, because you can simply say, atomically it did this, and you don't have to implement it at all. So that's nice. In any case, we found 6 bugs they injected, at least we think we did. And we also found one new bug where they had missed one statement in their code, which was really hard to notice. And their proof had that statement, but their code didn't. And it would occasionally segfault, and that was like really weird. But yeah, so we were able to find it thanks to our fuzzing and our checking of what the behavior was. Although the segfault honestly is findable without OmniLink, so I think that was actually a second bug we found with the segfault. And the new bug, actually, yeah, no, my bad. The segfault bug is not counted in the one because you can find that just by fuzzing their thing. The real bug that we found was another little omission which just made the trees go slightly out of sync in some absurd edge case, and it turns out like 200 steps in it found one. So there you go. And the last one, which I've actually talked about a lot, so I won't waste too much of your time on it. Yeah, Moody Camel concurrent queue. It has, oh, my bad, not 20,000, 10,000 stars. And again, this has been a surprisingly challenging project. It's got some nice documentation, and I've chatted with the maintainer a bit because we found a strange thing that it does. And it's on us to figure out what our results mean and tell them. But yeah, we've been investigating this, we've been writing the TLA plus for it, and our tool works on it. It's just an ongoing investigation. And we think we found a strange bug where you can enqueue 1, 2, 3, 4, 5, and then DQ 3, 4, 5, 1, 2, which is just like, what? Why? And this is a single enqueuer that does this, so you don't get to say, oh, well, I mean, if it was two different enqueuers, it's okay for them to come out of order. No, it just switched them. Why? And investigation pending, we're sort of in discussions with the author, but basically the claim is, if this is what actually happened, that's not supposed to happen. And if our tool is wrong, or our model is wrong, or a bunch of other stuff, then bets are off. And we're not quite sure, but it's interesting enough for that to be kind of a conversation. So that's neat. And in summary, we found this type of thing. And also, we wanted to check, linearizability checkers, those are a thing. You can download them. There's this thing called Porcupine. If you ever want to check some Go code, this is a real project. Again, it's actually quite popular. It's used in some distributed systems courses, not this one, but you can see it around. And we wanted to check how OmniLink performs compared to this. And I had every suspicion that OmniLink was actually a lot worse, and we would have to argue for relevance about the correctness specifications in Porcupine have to be written using just normal Go code, which has a lot of limitations in terms of analysis and stuff, like you can't cross-examine it as well because you don't have a model checker for it. But, I guess maybe it's a lot faster. And it sort of is. So we evaluated Porcupine using the BAT test and ran a bunch of traces on it. Let me just get to the graph. So it doesn't show up so well because of the graph scaling, but on small inputs, Porcupine absolutely destroys OmniLink. It is so much faster, like tens of seconds faster for the same input. But also, for invalid inputs, as you get to the interesting cases with hundreds of thousands of operations, Porcupine's algorithm just has some nasty edge case where it just sort of massively peaks its runtime. We're saying OmniLink here is the X's, and they're just all kind of fanning out here, just all boring-like. And then Porcupine is just massively peaking into minutes, which is crazy. And so it turns out there's this funny trade-off between using a model checker and how its algorithm works, and bespoke linearizability checking algorithms that have their own kind of line of research. And it turns out, I think it's something about reasoning about subsequences, where OmniLink reasons about states, where you have graphs and you can do merges, and I guess, yeah, our performance is just more predictable in a funny way. So that was neat. Oh, I guess I didn't have the other. Okay. I actually had a second graph in there, which I cut for time, but the crazy part is here, the invalid cases, the cases where Porcupine has to say, no, actually, take a very long time for Porcupine, but the valid cases are actually really fast. And then you look at the memory usage, and it's crazy because the valid cases for Porcupine massively peak into gigabytes of memory, and the invalid cases consume no memory. So it's funny, it's it's flip-flop. And in both cases, OmniLink is just more stable. And let's not talk about how it takes 10 gigabytes of memory to even run. It's a model checker. The thing is very chunky. But it keeps taking 10 gigabytes despite being fed more and more data. So that's strange, and possibly an artifact of Java heap allocation with the memory arenas and stuff. I'm not really sure, but it's interesting. So we did this whole analysis. We actually have 3 graphs in the paper, and I cut the other 2. I think I'll leave this as mostly kind of an interesting aside. There's a bunch of strange weaknesses that OmniLink has in terms of, well, it actually doesn't trust almost anything, but it gives you a lot of judgment calls. It has some interesting performance optimization opportunities. It can't reason about certain things that we just sort of ignore, like weak memory. And there's a bunch of potential future work about connecting it to these things. And I guess then we changed our mind because that's not what Brian's working on, nor is it what several of our other students are working on, because we ended up thinking that there's this thing called strong linearizability, which is a fun project, ask Brian. And as well, we should try it on distributed systems because we didn't actually port it away from concurrent systems, and TLA Plus is perfectly fine for distributed systems, but we haven't evaluated it and there may be some other issues. Likewise, we want to see if it works on things that aren't C and C++, like managed languages like Java or other fuzzers, like a thing called Fray, which is kind of same bucket as RR, but like different. So we've got a student working on that too. And yeah, basically that's the deal. OmniLink has this way of trying to solve the gap between TLA Plus and an implementation. We have a bunch of random stories and anecdotes about it, and we found some cool results. This was partly sponsored by MongoDB. Thank you, MongoDB, for that. And that is basically my content, and we have 4 minutes for random questions or whatever Tony would like to do. Yes.
Sleep a lot in this class.
Mm-hmm. Yes.
And mostly they're thinking about lunch.
Mm-hmm. That is fair. I should probably get lunch too. But yeah.
Well, thanks everybody. Thanks Finn for the talk. Hopefully you guys enjoyed it. He's actually over in the X-Wing, so if you want to go bug him, if you're looking to do some interesting work, you might want to talk to him. Apparently somebody has. Otherwise, I'll see you guys on Thursday.
Thank you.